Okay. We look at problem 8.64 of Sontag, in which ammonia is contained in a rigid sealed tank of unknown quality at 0 degrees Celsius. Okay. When heated in boiling water to 100 degrees Celsius, its pressure reaches 1200 kilopascal. Find the initial quality, the heat transfer, and the total entropy generation. Okay, so let us try to convert the wording of the problem into something which we can work with, some kind of schematics and mathematical derivations. So we have a rigid tank. Okay, so it's not insulated, my bad. So the tank is not insulated. Okay, it's a rigid tank, so the volume is constant, the specific volume remains constant. So NH state 1, NH3 is at 0 degrees Celsius and some X. State 2, when heated in boiling water to 100 degrees Celsius, its pressure so the final pressure is 1200 kilopascal. The temperature, it is heated to 100 degrees Celsius. Find the initial quality. So if we assume that the process taking place inside for the control mass is reversible, then the entropy of the final state must be equal to the entropy of the initial state. We know that the initial temperature T1 is equal to 0 degrees Celsius. If we know the entropy, then we can find out the entropy of the first state using the entropy of the second state, because we know the two quantities at the second state. So in a TS diagram, it may look something like this. Okay, this is state 1, this is state 2, this is at 0 degrees Celsius, this is at 100 degrees Celsius. Okay. Another consideration is that the total mass inside is constant, so the specific volume is also constant. So the specific volume second state should also yield the specific volume of the first state. Let's see how that pans out. As a matter of fact, the more fundamental, if it were a reversible process, this would be happening. If it was a reversible process. However, in general, it may not be a reversible process, and in that case the specific volume remains constant. That is the key. So if the specific volume is constant, we know the final specific volume because we know the temperature and we know the pressure. If that is equal to the initial specific volume, then the T1 is known and the specific volume will be known, which will help us to find out the X. Okay, so on a PV diagram, this would be the process. The mass and the volume are constant, that is why the final specific volume is also constant. So the entropy would be equal in the special case when there is no irreversibility, that is the process is reversible, but in general it may be irreversible. Let's see if the process is truly reversible or not, because in the question it has been asked to find the total entropy generation. We expect that the process will not be reversible. However, if it is indeed reversible, then S2 minus S1 should be 0. Rather, S2 minus S1 plus all the heat transfer, or rather the S2 minus S1 should be 0. So state 1, T1 is equal to 0, that is all. State 2, T2 is equal to 1200, T2 is equal to 100. So the specific volume at state 2 is equal to volume of ammonia T equal to T2 and P equal to P2. So the specific volume at state 1 is equal to the specific volume at state 2. So the quality at state 1 is equal to quality of ammonia at T equal to T1, V equal to specific volume at state 1. This will give us the this is problem 864. The initial quality is 0.4952. What is the what is the initial quality? The initial quality is 0.495. What is the heat transfer to the ammonia, and what is the total entropy production? So because the volume is fixed, volume is rigid, work done equal to 0. What is the mass content in the system? The mass content in the system is to be found out from the mass content. We don't have any information about the volume. We have the information about the specific volume, but we don't have. Okay, let's do the calculation as in terms of specific quantities. So the U2 minus U1 plus W12 is equal to Q12, but Q1, so what is Q12 equal to? What is Q12 equal to? So the initial quality, so the initial states are known using the first law. Q12 is equal to U2 minus U1 plus W12. So the W12 is set to 0. And we write down what the U2 is, int energy of ammonia at T equal to T2, P equal to P2. Similarly, this will be int energy of ammonia at T equal to T1, P equal to specific volume at 1. Okay, using this we find out what the total amount of. Okay, there is something wrong. Okay, what is wrong? So U1 and U2 we have redefined. Okay, we have to make that correct. Okay, there we are. So the heat transfer is 741.8 kilojoule per kg. Now we must find out the total entropy generation. The total entropy generation. So the equation to do that is derived from the second law, which is S2 minus S1 is equal to. So S2 minus S1 is the. So if we consider the entire system as our control mass, so this is the rigid box which is heated by boiling water. It's not heated by a burner. There is boiling water. So the total entropy of the system is equal to S2 minus S1 is equal to delta S gen. So delta Sgen is equal to the entropy change of this control mass plus the entropy change of this. The change of entropy of the control mass is this. The change in entropy of the surrounding is equal to the heat lost. So because of this heat transfer, the entropy change is this. Okay. But because of this heat transfer, the entropy change of the surrounding will be equal to what? This will be equal to minus of Q12 divided by T boiling, where T boiling is 100 degrees Celsius plus 273.16. So the control mass changes its state from 2 to 1 because of the heat transfer. The change in entropy because of this heat finite temperature difference is accounted in this term. So the total entropy change delta S Cm plus delta S surroundings. So there's another mistake. S2 S1. We have not yet defined the entropies. It's the entropy, the initial state. Okay. So the total change in entropy is equal to 0.5447 kilojoule per kg Kelvin. So the concept is simple. Because of the change in state, we know that regardless, so because of the change in state from 1 to 2, regardless of the process, S2 minus S1 is the change in entropy, regardless of the process, because S is a state property. So if we know the change in entropy of the process, we must know the entropy generation, total entropy generation, not just for the process. The total entropy generation is equal to the entropy increase of this control mass due to absorbing heat. But what if the system is absorbing heat equal to Q, then the surrounding is losing heat equal to minus Q? The entropy change of the boiling water is equal to minus of Q12 by T. This minus sign comes because the heat absorbed by the control mass is equal to negative of the heat released by the surrounding. So this gives us the estimate of the total entropy. Okay.